Okay, everybody, let's get talking about the last set of algorithms for milestone 3. So you're wondering, when are these algorithms going to stop? They're stopping today. So we're getting all the way to the best algorithms we're going to talk about. And again, they all build on top of each other. So don't worry if you're going, wait a sec, does that mean I didn't have to pay any attention to any of the other stuff? Nope, you did. So it's good you were here. Okay, so at the very end of Monday's lecture, we saw Dijkstra's algorithm works pretty well, but it does do some wasted work. Kind of looks in all directions, and the direction that's away from your destination is kind of unlikely to actually lead you to the right path. So we are wasting some time. People came up with some ideas. How can we speed that up? Which were basically pruning functions. What if we don't look at nodes that are going in the wrong direction? And we saw that could speed things up, but it's going to risk us not finding any paths sometimes. For example, if we're trying to cross the 401, or getting suboptimal paths. So it's a little too aggressive. We just say, we'll never look at something that's in the wrong direction. Well, maybe that is the right way to get on the freeway and get to your destination. So we're going to try something a little different to speed it up. Same idea, but it's a little more gentle. And these are called astar algorithms. Okay, so these are enhancements to Dijkstra's algorithm. So kind of walking through the algorithms we've looked at, Dijkstra's algorithm is an enhancement to breadth first search. So it's almost the same code, just changes how you sort your wavefront. Astar is an enhancement to Dijkstra's algorithm. It's not much more code. So you basically write Dijkstra's algorithm and you add a little bit more and you've got astar. You just have to think about what is that code. Okay, so they're enhancements to Dijkstra's algorithm. They use what are called domain-specific heuristics. Okay, so a bunch of words there. Heuristic. Anybody know what heuristic means? What's the definition of heuristic? Take a guess. That's almost the definition of a heuristic. Take a guess, right? So heuristic is just like a good idea. You can't prove it's the best thing to do, but a heuristic is like, well, this seems like a good idea. Domain-specific means we're making use of some knowledge we have of the problem. Okay, so the problems we're solving can be encoded as graph problems, so can tons of things. We're not just going to use the fact that our problem is a graph, we're going to use the fact that it's a city map. We know something extra. It's not just nodes and edges, they're intersections, and we know what those intersections are. And there's street segments which represent actual roads. So we know something about this graph. So the fact that we're working in a map, not just an arbitrary graph, but a map where we know where the nodes are, means we can estimate, are we getting closer to the destination or are we getting further? You can't always do that. So if I give you like a social network graph, just a graph that, this huge graph of 1 billion nodes that Facebook has, you don't know whether you're getting closer or further from your friends, unless you have some additional information. But we do know that additional information for our street map. We can use our locations. Okay, so we're going to take this extra knowledge that we have, and we're going to try to come up with a way that we can incorporate that into our wavefront sorting or our wavefront ordering. And the idea is we're going to have something that's very close to Dijkstra's algorithm, almost the same code, but we want to look at the most promising solutions first. So these heuristics, these astar heuristics or astar algorithms, are often called best first search. Okay, so we started with depth first, which was recursive. It kind of went in random places. Breadth first was more organized, went out in circles. Dijkstra was a bit more organized still for shortest path because it's sorting by what's the travel time to every node. And astar algorithms are a little more sophisticated still. So they're trying to look at the most promising nodes in the wavefront first. Look at those most promising solutions and kind of expand the wavefront out from them. Okay, so Dijkstra's algorithm, remember, it kind of expanded out in circles. Looked like that, okay? And when one of those circles hit the destination, we were done. So what astar does is it expands outwards. If we've got a good heuristic, a good way of sorting the wavefront, it'll expand outwards in something that's not quite circular anymore. It prefers to go towards the destination, but it will still search some in the opposite direction and out to the sides in order to check, well, maybe I'm right near a freeway. Maybe I should look around me a little bit to see that might give me a better solution. Okay, just like Dijkstra's algorithm, it hits the destination, we invoke a backtrace algorithm, we find the path. Okay, so the only difference from Dijkstra's algorithm is the order in which we sort our wavefront, and hence where are we searching. Okay, and it will mostly search in the right direction, but not completely. And that's on purpose, because if we said we'll only search, in this box, that was one of the ideas on Monday, it was too limiting. Sometimes the best solution might be a freeway out here. So we didn't want to be that extreme. Okay. Okay, so how can we do this? So any ideas? So we're not using pruning, we're instead using sorting. It's more gentle. We want to sort our wavefront. So remember, Dijkstra's algorithm sorts the wavefront by travel time, what I'm calling best time. Okay, best time that's the time it took me to get to this node in the best path that I explored. Okay, so I've started at the source. I've already gone and done a bunch of wavefront expansion. Okay, so I've gone through that while loop where I'm putting things on the wavefront and taking them off a bunch of times. And what I want to look at right now are I've got two nodes in my wavefront, this one and this one. And I know what the best time I ever found to both of them is, because that's what I've been keeping track of in my Dijkstra's algorithm. So I know that the best time to this one, node 2, is 45 seconds. And I know the best time that I found to this one, node 1, is 30 seconds. Okay, if I'm using Dijkstra's algorithm, which of these nodes am I going to look at next and go get all of its neighbors and put them in the wavefront? Okay, so if these are both in the wavefront, that's my whole wavefront. Which of these two am I going to look at next with Dijkstra's algorithm? This is not a hard question. Okay, so if you're just going, that seems too easy. No, it really is that easy. It's not a trap. Okay, so anybody have any ideas? So C09, I'm going to go to you. Whoops, let me unmute you. Go ahead. Right. Yeah, so Dijkstra's is exactly right. Dijkstra's algorithm is going to look at N1 first, because it's got the lower travel time. But we can look at that, and with our superior high-level human intelligence, we can say, that doesn't look like the smartest thing to look at. It seems like I should look at N2 first, because, yeah, it's got a bit more travel time, but it's way closer to my destination. I think that's going to lead me to a good place. Okay, so we got to change something. We have to change how we sort the wavefronts so that if we think N2 is a better solution, that's the next one we should look at. What should we do? So that's the next one we take off the wavefront. Okay, it doesn't have to be a lot of code. We just want to change how are we going to sort the wavefront. Okay, so C09, actually, I forgot to turn your mic off. You're still on.
Yes, so for each entry in the waveform, we can compute the score based on the heuristics we want. Maybe assign different heuristics.
Okay. Okay, so we're going to compute a total score, and we're going to sort on that. Okay, that makes sense. Now the question is, what would make sense for that score? Like, what should I put into it? Okay, so yeah, I do want this score for N2 to be less than the score for N1. So what can I put in that's going to make that true? That makes some sense. So I'm going to go to A11. So it's okay, A11, you're on the air. Okay, so basically use the distance. Is that right? Okay, so you're saying take this, and we can compute that distance pretty easily. In fact, in M1, you wrote a function, find distance between 2 points. So for these two intersections, I can find this distance. So I've got, let's call that distance 2. I can also compute this distance. Let's call that distance 1. So you're saying maybe sort on those distances. Okay, so we could say score equals distance to destination. Okay, it's reasonable. So that means that we're going to look at N2 first. And that seems like a reasonable thing to do. And let's say I do that. So let me erase all this. Okay, so let's say I've got another solution here, though. So let me put another one in, N3. Okay, so let's say N3, let me make it look a little different. Okay, so N3 is here. Okay, so it is a little bit further away from my destination. But let's say N3 is only 40 seconds in travel time so far. Should I look at N3 or should I look at N2? It's not quite clear, right? According to the distance function, I'm going to look at N2. And then let's say if I look at N2, I find, well, I can get to this node, which is even closer. And then this node, which is even closer. And then this node, and this node, and this node. I could go all the way to the destination, and I'll never look at N3. Okay, so that actually can be a bit dangerous. Because what if the best travel path actually went through N3? It was a little further away, but it actually had a lower travel time. And I totally ignored the fact that it had a total travel time. So this also could cause me problems. So what you just created is called a directed search. It's basically a variation on astar, but it's not guaranteed to get the best answer. So if I use distance as my metric, it's not a bad idea, but it might not get me the best answer. And for milestone 3, we really want you to get the best answer. So best answer is most important, then getting it in a good CPU time is second most important. Okay, so good idea. So try distance, but distance as our sorting function has this problem of may not give the best answer. And the reason was we're not paying any attention to how much travel time have we taken so far. There's kind of two things we want to look at. How much time is it taking to get to the node I'm at right now? And how far away am I from the destination? And if we just use the distance to the destination, we're only kind of paying attention to one thing. We're not paying attention to how long it took me to get where I am right now. Okay, but still, a good idea. It's the right idea. Any tweaks on that? So let me clear this. So, okay, let me go to, sorry, 07, I cleared you. Okay, you're on the air now.
I'm thinking about something like travel time multiplied by the inverse of the distance. Because the closer we are to the destination, the more we care about how much time that pass take. But we are probably also consider about the distance.
Okay. Okay, so I'm going to try to capture that. So I think you're saying, let's try to combine these things. So let's take the travel time so far, and I've called that best time. Best time to the node I'm at, and I know it, okay? This is not a guess. I know that for sure because I've been keeping track of it as I went through all the nodes to this point. And you're saying you want to multiply that by the distance to the destination. Okay, and now the idea is that if one of those is really small, you like it. And if they're both really big, you don't like it. Does that make sense? Yeah, so it's not a bad idea. This could also work. If you walk through it though, you're gonna find that I can produce cases where it's not gonna get the best answer either. Because the function it's a little bit tricky to think about. You know, you're basically multiplying distance times time. And I'm not going to show you a counter example right now, but I can come up with examples where that's not going to get me the best path either. This multiplying is actually a good idea when the units don't match, right? So my distance and my time, the units don't match, so multiplying them is probably better than adding them. Any other ideas? So it's not a bad idea at all, but that one's not going to quite work either. And if not, fear not, I have an idea. Okay, so we'll go on to my idea. Yeah, so B06. What do you think?
We add a little bit of depth first. So we want to add one or two nodes, estimated qualifier.
Okay. Oh, sorry, I don't have your microphone on. Why don't you just say that again quickly? Sorry.
We use a little bit of depth first to
Yeah, you could try that. Okay, so your idea is like do some depth first search, some local search around there. It's probably not going to speed things up because the thing about depth search first search is it's pretty undirected. So you're kind of, it just kind of walks around recursively and kind of randomly. So I'm at a node and now I do a local depth first search, which I don't have much control over. So it's probably not going to make things faster. And I also risk not getting the best path. Okay, so here's my idea. So this multiplication is a good idea if you don't have the same units, because it's just hard to add things. What if I had the same units? The units of this best time, that's my known travel time to this point, are seconds. Could I get something else, which is units of seconds, to the destination? Because then I can just add them. And I add two things together with the same units. That's a well-formed number. I could sort on that. So what do you think? Could I get something with units of seconds that is meaningful from, I know I'm at node N2, and I want to get to the destination. So let's see. How about that? We'll go to you in a second. I'm going to give anybody else a chance. If there's anyone else who wants to take a shot at this, buzz in now. Okay, I see C07, you're thinking about it. Are you thinking about it, C07, or not? I think you're thinking about it. Do you want to go for it? All right. I've decided you're going for it. What do you think? Seems like you have an idea. Say it really loud. Oh, actually, I've screwed up the mic. So go ahead. Yeah, so that's a really good idea. Okay, so we take best time and we add to it an estimate of remaining travel time. Okay, and that's actually going to work really well. These things have the same units, we can sort on it, it's a good idea. Now, we need this estimate of remaining travel time. We want to get it pretty fast. The whole point of this is to speed things up. So if we spend a really long time getting this estimate, it's not a great idea. We can compute this distance quickly. Okay, we have this find paths or find distance between 2 points functions from M1. And if you look at it, it's not that much math. Okay, so it's pretty fast. But to get travel time, we're also going to have to guess how fast could we drive. Well, so I'll leave it to you to figure out what is a reasonable estimate, okay? But you can come up with reasonable estimates of the remaining travel time pretty quickly. You don't want to do anything really complicated because it's probably too slow, and you'd be better off just exploring more nodes, because that's always an option. If your heuristic, this estimator is not quite as accurate, well, you can always look at more nodes. So you want something that's reasonably accurate, but also fast to compute. Now, I guess I'll leave it to you guys to figure that out. Okay, so let's say, here's my idea. Okay, so my idea for the distance function is I'm going to say that cities are linear. So I'm going to get the distance in the x direction. Then I'm going to add the distance in the y direction. So I'm going to assume there's no 45-degree angle streets, because I don't think there are that many. So I made that assumption. And then I'm going to divide by, I don't know, I think in most cities that the average speed limit is about 60 kilometers an hour. So I'm going to get delta x, I'm going to get delta y, and I'm going to say the remaining time is equal to, let's say, delta x plus delta y divided by 60 kilometers. And I'll get the units right, okay? So I'll make it all the same units. So 60 kilometers per hour. And I'll get this, but I'll put that in meters per second. And I could use that as my heuristic. And now my sorting function could be best time plus remaining time. What do you think of this idea? It's not bad, okay? But do you see any problems with it? For that, so I'm going to go B09. Yeah, go ahead.
So one issue I can see is that it probably like the speed limit in summer maybe significantly lower than 50 kilometers per hour, and there are also some kind of there will be like critical roads that like the N2 is kind of far with it.
Yeah, okay, so the problem you see is, the speed limits may not be very accurate. I'm high sometimes, I'm low other times. I also was basically this delta x plus delta y, it's not a terrible estimate, but if there are 45-degree angle roads, well, then it also might be an overestimate, okay? Let's take a look and see, we can't get this estimate perfect, okay? So trying to get a perfect estimate is not going to work, it'll take you too long. So it has to be something you can compute pretty quickly. So on the plus side, what I computed there, I can do pretty fast. On the minus side, it's not that accurate. Let's see if that really matters. So let's say that this estimate that I just gave over-predicted my delay, okay? So let's say from here, it predicted, it will tend to over-predict delay. I'm assuming, sometimes it might under-predict, but sometimes it can over-predict as well, right? There might be 45-degree angle roads, there might be 100-kilometer-an-hour streets. Let's look at the case where I over-predict. So I think my remaining time is 50 seconds, and really it's only 30. So let's say here, I think that I've got 50 seconds left. That's what I get when I run this, this heuristic. And let's say here that I think I've only got 30 seconds left. Okay, so now the total of this is 75. I'm going to work on N2. So that sounds good. I wanted that. Okay. And as I go through N2, I'm going to keep putting new nodes on. So maybe I put a new node on. Actually, let's make this one like 60 seconds. Okay, so it's like not even close. So I think that my remaining time here is 30 seconds. So 30 plus 45 is 75. We'll look at that next. And now I find a new node, N3, that I can reach from this one. And N3 has, let's say it has a known time of 50 seconds. And our estimated time to get to the end is, let's see what I say, it was 30 seconds before. Let's say it's 25 seconds now. Okay, so that's 85 seconds. And, no, 75 seconds. Okay, so I'm going to take that one next. And let's see, that keeps happening. I keep pulling more nodes off, and each of them, I add up the estimated time plus the time to it, and it keeps looking like the best choice. I'll go all the way here, I'll get to the destination, okay? Then I'll invoke my backtrace, and I'll get the path. So it was pretty efficient. It did drive me towards the destination. That's all good. The case you have to worry about is, okay, so remember that the estimate here was 30 seconds. Let's say that this node is right by Highway 401. So there's a really fast highway here, okay? And let's actually say it even goes on an angle. So it almost goes to the destination. And the speed limit on that is 100 kilometers per hour. Okay, so I was estimating that was going to take 60 seconds, but let's say after I take this into consideration, it really takes 40 seconds. Okay, so that means that I could actually take this node and then a sequence of nodes along this Highway 401 that gets me there in only 70 seconds. Okay, and this other path took me 75. I didn't find the best path. Okay, so my heuristic kind of led me astray still. I got there pretty quickly, that's good, but I didn't find the shortest path. I failed the optimality test, that's bad. Does this mean I don't want to throw away this idea? I still like this sorting idea. That's why I showed it to you. What has this taught me? Is there anything I should learn from this? So what went wrong? Okay, why did I get a path that is not optimal? Okay, so there's a behavior here that happened that is what led me astray. Okay, so I'm going to go to A07. Yeah, go ahead.
So the second case, there is a near optimal solution, but it's not the exact optimal, and the algorithm will fail that thing and then go to the actual productized fast solution. So maybe we can make the median time dynamic depending on the surrounding of the certain node.
Okay, so I didn't catch it. So you're right. The problem was, I'm going to repeat part of what you said. The problem is, yeah, we never looked at the optimal solution. We were feeling too good about our solution from N2 and all the nodes that came after it. And they made us discount this other node. We never went back and actually looked at it. And if we had looked at it, gone a bit further exploring, we would have found a better path. Question is, how can I fix that? Not sure? Okay, so I'm going to go on to B09. What do you think? Do you know, or are you just buzzed in from the last one? Okay, I'm going to go to the next person. C09, do you know how to fix it? Buzzed in for the last one. Okay, so it's a jump ball. Anybody know how to fix this? Okay, it looks like B06, you got an idea. Let's go to you. Go ahead. How would you fix this? So say it really loud. I'm having trouble hearing you.
It's something like a triangle model where it's the time it's like less equal to multiply the highway girl that gets
Okay, so your challenge, so you're suggesting maybe we have a trade-off model, we consider multiple possibilities for over here. Your challenge is you don't know that you're right by a highway. You don't know you're right by a highway until you actually do some more expansion of nodes through the graph. If you do some more expansion, you pull things off the wavefront, you look at their neighbors, you'll find you're by a highway. Thing is, you're never going to do that if your sorting function was so aggressive, so optimistic. Well, not optimistic, sorry. If your sorting function made you keep looking along this path, you just never went back and looked here. But it's not easy to actually say I'm near a highway. There are actually techniques to do that, but it involves pre-processing a graph. It's actually a lot of work, so you can do that, but it's beyond what we expect. So there's a relatively simple thing you can do that will fix this. It's going to cost you some CPU time. Okay, we're not going to fix this without spending some more time searching, but that's okay. Okay, what we want is an algorithm guaranteed to get the right answer. That's the first constraint. So we're not there yet. What can we do that's pretty easy, that's going to get us the right answer, but slow us down? So I'm going to go to A07 again. What do you think? And say it really loud.
We can probably like have a bit of representing that the location of the highway and the source to the destination. The distance between the source and destination is larger than the distance between the source and the nearest highway or station highway.
Okay, so I'm going to stop you there. So you've got, these are good ideas, but they're complicated. You're saying make a grid so you kind of know where the highways are and so on. This might actually lead you to a very fast solution. So you could do that. Don't do it first though, because it's complicated. So something that is simpler. And I see A11. I'm going to go to A11. What do you think? Yeah, you could do that. Okay, so once I get to the destination, I could keep searching, although that's going to destroy my time. Because if what makes astar faster than Dijkstra is once I hit the destination, I stop. If I just keep searching till my wavefront is empty, I've actually done all the work that Dijkstra would have done, right? Even like the most work Dijkstra could do. So, yeah. Did everybody hear that? Okay, so that is a key insight. What led me astray here is that I overestimated the remaining time. Okay, I estimated that the time from this point, I think the number I put in was 50, I think I put in 60 seconds actually, and that was an overestimate, which made me pessimistic about what's going to happen from this node versus what would really happen. So I never looked at it. If I have an underestimate, then I will always look at every node that has any possible chance of being on my best path. Okay, so make sure you do not want this guess to just be your best guess. Okay, if you just wanted the fastest path search algorithm and didn't have to get the best answers, okay, then that's reasonable. That's called a directed search technique. But if I want you to get the best answer, and that's what I want, you must guess, never guess high. Okay, if you never guess high, then what that means is you would guess that the future time from here, instead of saying it was 60 seconds, you might say, well, I think it's 30. And that's probably too low, but it's okay. And the future time from here, you might say is 20. You're going to still explore from N2 for a while, but as you explore, you're finding, okay, now my known time, this best time is 65 seconds, and my estimate of the future is 10 seconds. All right, so my total time estimate is 75. That's actually now more than this total time estimate. So I'm going to start looking from here. And when I start looking from here, I find the highway 401 and I start looking along it and I'll get to my destination with the shortest path. Okay, so the key is do not overestimate. Now, if you made your, okay, so here's what if you then say, okay, I'm going to always estimate 0. Okay, so I've got a really simple underestimate, right? My remaining time, I'm going to estimate 0. You can actually do that. What algorithm do you get if you just estimate the remaining time is always 0? You get Dijkstra. Okay, so Dijkstra is actually a special case of astar, where you just always estimate that the remaining time is 0. And it's perfectly valid. You will, in fact, get the right answer. But if you can give a better estimate, bigger than 0, that is still always, never overestimates, you can get the best path and you can get it faster. Okay? And the bigger your estimate is, while still never overestimating, the faster your algorithm gets, because the less sort of random searching it does. It's more focused on the most promising solutions. Okay, so does that make sense? You also want your estimates to be pretty fast. So, and not take you forever to code. So don't start off with, here's the most complicated thing I could think of to code. I'm going to go for it, or even better, I'm going to assign it to my teammate. So I'm going to give it to Dr. Tallman. I've sketched out a super complicated algorithm on a whiteboard, and then I basically get to the wiki, I assign it to him, and I take off. Don't do that, okay? Okay, so how do we implement this? We are changing the wavefront sorting. We are not changing that best time that we're recording at a node. That still has to be accurate, okay? We're sorting on a guess. We don't want to update our best time to a node with anything except this is the known time for sure from the source to this node, okay? So our wave, whoops, sorry. Our wave element, so this is the structure that I've been using to make my wavefront. Okay, so we built up that we need to have a node. We need to have an edge ID so we can backtrace. We have a travel time, okay, which is the best travel time from the source to me. We had all that before for Dijkstra. We're adding one more thing. Whoops, sorry about that. We're adding one more thing, this new value that we're going to sort on, okay? And we're going to tell our priority queue that that's what we're sorting on. And that's going to turn us into astar. Does that make sense? So you got to come up with those heuristics of, well, how are you going to get that value to sort on yourself? Yeah, go ahead.
Just to clarify, that double travel time is best time, right?
This one, I used 2 different names. Okay, so in my node data structure, there's another data structure that I had called node, of basically number of intersections. It was like a vector. I'm kind of making up notation here, but I had a data structure I called node, and in it, I had an entry for every single intersection. It had a best time in it. Does that make sense? Now, I updated that best time from this travel time when I took things off the wavefront. So the reason I don't call it best time when it's in the wavefront is I might have the same node in the wavefront multiple times. That's something you want your code to handle. Don't assume that if I put node 33 in the wavefront, that I never put it in again. You might. And one of them might be a better path than the other. The one that is the better path should come out of the wavefront first, but the other one might still be there. So you want to make sure that when it comes off the wavefront, you don't mess things up. So that's why I just called it travel time in the wavefront. Does that make sense? But yeah, the short answer is it's pretty much best time. I just gave it a different name to be clear. Okay. I'm going to just quickly demo this then. Let's see if I can find my VM. Okay, so here's my okay, let's go through the algorithms again, just because it's fun. Okay, so here's depth first. Chaotic, explores all over the place. Went to breadth first, gets the right answer, but slow, right? It's doing all this re-expansion. Okay, so let's get rid of that. So now Dijkstra is pretty fast. Okay. Well, not as fast as I'd like, but I actually got a delay loop in here. Okay, so Dijkstra's eventually going to find where I was, and it's way better than breadth first. And now I'm going to switch it to A star. Okay, so if I do A star, you notice that it's kind of moving toward, it's exploring in multiple directions, but mostly towards where I clicked. Okay, and it found the right path. Let me do that again. So I go over here. I'm pretty far away, but you notice it was pretty correct in going mostly the right direction. Okay, and this is slowed down for animation. So the actual algorithm is much faster than this. I'm basically slowing down the graphics on purpose. Okay, so let me show it one more time. So yeah, A star, let me go this way. Okay, we got there pretty fast. And if I turn that into Dijkstra and go back the other way, it's a lot slower. Okay, in this case, now in this case I picked near a highway, so this actually helps A star quite a bit. But you see, Dijkstra's doing a lot of wasted work. It ultimately finds the same answer, but it explored in a lot more directions. All right, so let me shrink that down. Okay, so that's it for algorithms. So the best algorithm that I've shown you is A star, but it's almost exactly the same code as Dijkstra. So you're going to code that up, try to make it pass all the performance tests. Okay, so let me talk about some tips. Okay, there are a whole bunch of tests. So who started on milestone 3? Okay, I think most people are still working on OP1. Okay, one team, great. So it's not unexpected. Don't leave it to the last couple of days. It's pretty stressful. Okay, remember you probably made some resolutions after M2. Live those resolutions. Start this weekend anyway. You want to start passing the simplest tests first. So the first tests here are called path cost. Path cost just checks that you understand our specification of what the delay of a path is. It's easy, but if you can't pass that, it means you don't understand the specification. So make sure you pass that. Then we have some tests that are called simple legality, okay? So simple legality means we put intersections very close together. Okay, so they're only one intersection apart, maybe two intersections apart, and we're only checking you get a legal path, not that you get the best path. Pass those. The reason is if you fail on one of those tests, you can bring it up in the debugger, and you know it's only one or two intersections away. It doesn't take that long to watch the debugger, watch everything your algorithm's doing, and see where you went wrong. Okay, then we have these legality tests. Okay, so here's another legality test, but it doesn't say simple. Legality tests can be far apart, right? So it could be halfway across the map. These algorithms are going to move a lot of data when they're doing intersections that are far apart. So it's harder to debug that case. So that's why you want to do the simple one first. Once you pass those, you go on to the simple optimality cases. Okay, so this one, for example, is simple optimality. So that's checking not just is the path legal, but is it either the shortest or close to the shortest? We give you some margin. And it's for intersections that are close to each other. So again, you can run them in a debugger, you can watch what happens, easier to debug. Then on to the optimality ones, which are farther apart. So if something goes wrong, more work to figure it out. And then on to the performance tests. Okay, so there's a medium performance, a hard performance, a very hard performance for Toronto and also for London. The only difference is they basically just get tighter CPU limits. So medium with not a very good algorithm, you could pass it. Hard, algorithm has to be a bit better. Very hard, algorithm has to be a bit better still. I've shown you all the algorithms you need. You just have to code them up pretty well and you'll be fine. Okay, so this is just highlighting why are those simple cases easier to debug. They're basically intersections that are right beside each other or maybe sometimes two intersections away. So you can just watch those run in the debugger. You know exactly what should happen, see if that happens or not. Okay, after you make sure that, so you can look at the test cases and you can, in your use your user interface to see where are these intersections. And you can even make your own test case. Once you pass a case where the intersections are right beside each other, try one where there's one intersection in between. So they're just 2 units apart. Okay, again, you can watch that run in the debugger. Okay, so you're doing the smallest test first. This is the way you should test. Okay, and then you get into the more general cases, these legality and optimality cases that are maybe halfway across the map. There are, inside those tests, there are tests that have a turn penalty of 0. They're a little bit easier, because if your turn penalty code doesn't work, or there's some weakness in your algorithm with turn penalties, it's not going to affect you. So see, do you pass all the ones with turn penalty equal to 0? If not, work on those first. After you have those working, are you failing some that have turn penalty not equal to 0? So these are all ways to kind of get code working a little bit at a time on an algorithm. Okay, so there's lots of room for messing up memory. So run valgrind. We put St. Helena in the EC297 exercise test, so it's easy for you to run valgrind on it. Just run that test, it'll do everything for you. Debug check is also your friend. It checks memory just like valgrind. It also checks that your STL containers are valid. So you've already seen that it checks for vectors if you're going out of bounds and so on. Something that it checks that is quite useful in this milestone is if you're using a priority queue or you directly use a heap, which is what priority queue is built on, there are ways you can insert bugs in your code where you break your heap or you break your priority queue. Okay, so the priority queue assumes that you push things in with just push, you take them out with pop, and the priority queue will keep things sorted. There are ways you can break that. If you just start shoving data into the middle of the container, if you have pointers to the stuff in that container and you start going in and changing their values, you can break the priority queue because it won't be a heap anymore. The STL debug check build, it will actually check if it's a heap. So it's way slower because every time you do anything with the priority queue, it'll actually check if it's still a heap. But if you ever do anything like that, it'll tell you. And teams do that all the time. The most common one is they basically, without thinking about it, they have pointers to some of the stuff they put in the priority queue, and they just go in and start updating values. And you can't do that because if you start updating what you sorted on, it's not a heap anymore, right? It's not in the right structure. So put it in with push, take it out with pop, and don't change the value you're sorting on in between. Which if you don't have pointers lying around, you won't do. Okay, so pointers are sort of temptation if I could just poke some data here or there. Okay, once you have all of those tests passing for optimality and legality, you want to do speed tuning. The first thing you want to do is make your algorithm good. So that's what we've been talking about the last few lectures. Then you want to think about your data structures, use a priority queue, use vectors where appropriate, etc. And then last, you want to think about low-level code, which you probably won't have to think about much. That's just mostly, did you do any deep copies of big things? That's usually the thing that might get you in low-level code. You don't have to go any further than that. Okay, so as you get to finding these cases that go all the way across the map, it's hard to watch that in the debugger because it is, if it looks through 100,000 intersections, that's going to be a long time watching that while loop actually execute. You're going to get bored before you get to the 100,000th thing. And there will be cases where it's actually going through 100,000 intersections. So you can see what's going on though by using graphics. People are visual computers. We are really good at vision compared to how good we are at text. So you can animate your algorithms. If you do that, turn it off in your final submission. We do disable the graphics, so even if you forget, it'll probably be okay. But just in case it slows down your submission or causes some problems, if you visualize, turn it off in your final submission. Okay, so how would you do that? This is the heart of the code that I was using to visualize algorithms there. It's not very complicated. I basically made a define called visualize. That means if I want to turn off this code, all I have to do is comment out one line. Okay, so I comment out that line and all this code will be removed. So that's how I have my nice safety, take it out in case it's slowing my algorithm down. And all I did is I said, give me the renderer, okay? So whoever's talking back there is actually pretty distracting, so. All right, so I'm gonna highlight the street segment. So let's say I'm searching to the next node. I know what edge I used to reach it. I can draw that. So I'm drawing the street segment here and I decided to draw it in blue. So I'm not showing you this helper function, but it's easy to write. You probably wrote something like this already for milestone 2. Draw a street segment. I need to make an update right away, so I call flush drawing to say I need this graphics on the screen right now. And then I need to delay. If I just draw as fast as I can, I probably won't really see it. So I'm delaying by 50 milliseconds. And here's a little helper function I wrote that delays by however many milliseconds you pass in. So I basically just made a chrono object that is the right number of milliseconds. And this is a call that says, put my thread, this is the main thread of my program. Every program has at least one thread in it. Put it to sleep, which means don't do anything, for that many milliseconds. Okay, so it's just a simple two-line function. This will delay by however many milliseconds I pass in. So if you put this code in, you can visualize your algorithm. In tutorial 8, we talked about how to profile your code, how to time it. So you can also see where does the time go if you're not passing the performance tests. And go watch that tutorial for the details. But basically, you can use either the profile build or the release build. And it's really easy to profile. Go to that tutorial and see it. The release build, you get the full picture of where your time goes in your program. But because functions have been inlined, which means we've taken the compiler has taken small functions and pasted them into big functions, your information won't be quite as detailed. Some of your little functions just won't show up. They'll be embedded in the big functions. Profile build, you get more detailed information. There's no function inlining, so you'll get timing information on every single function. But it means that your little functions are going to show up as somewhat more time consuming than they really are, because in release build, those little functions would have been pasted into the body of the big function by the compiler, because that's faster. It's avoiding the function call overhead. Anyway, more in tutorial 8. And this is actually an example from our reference solution for milestone 3, just where does the time go? Okay, so last 2 slides, I'm just going to show you. At the very start of milestone 3, I talked about how past search algorithms were important in a whole bunch of areas. I'm going to dive in on integrated circuits because that's actually my research area. I'm actually maybe shocked to know this, but I'm actually not just purely a software guy. I actually design computer chips. So in integrated circuits, we actually need fast path search algorithms. So this is a picture of Stratix 4. That's actually the last chip that I helped architect before I left Altera. And this one has 4 billion transistors. And I took this picture with me, which is why I'm showing a picture of it, because I couldn't find good pictures of recent chips. The latest chip from Intel, which now owns Altera, in FPGAs is Stratix 10. It's 43 billion transistors. Okay, so this one's already complicated enough, 4 billion. Now it's up to 43 billion. I wrote out the numbers because we just lose perspective on how many transistors that is. Okay, so those form 10 million logic elements, basically little lookup tables and a bunch of other stuff. We need to make connections between the inputs and outputs of all those things, and not once. This is actually what happens when you program one of these chips. So every engineer who's using one of these chips, every time they compile their design, they're actually making about 40 million connections, signal paths from the output of this LUT to the input of this RAM and so on. And they're doing that in a graph, which basically is a little piece of that graph. A graph that has about 300 million nodes, so much bigger than any, if you thought Tokyo was big, this is about 300 times bigger than Tokyo for this course. Every node is a wire that's been built on the chip. Every edge is a switch that can be programmed to connect things. So you have to search through this, and you have to do it pretty fast, right? This engineer's in a hurry. This actually takes, with good algorithms, this will take about an hour, maybe 2, maybe 3. And the engineers are really annoyed by that. Trust me, like I was on Altera for years, but they kept making this faster, but the chips kept getting bigger, and the customers were always annoyed. But it's kind of an amazing thing that you can actually do this many path searches. They have to find shortest paths with all sorts of constraints. They can't be overlapping and so on, really short together. So you need really fast algorithms. So I actually use one step beyond astar. You know, those directed searches where I said, okay, our heuristic is not going to be for sure an underestimate. So we're going to accept we might get a suboptimal answer, but we need it faster. Those are the kind of algorithms we're using here. Directed searches, because we can't guarantee optimal. We're just trying to make it good. Okay, so that's pretty big. And you actually, a lot of you might go, many of you may go to PEYs at Intel and actually work on those tools. So those tools are developed just off the edge of the University of Toronto campus, right? So there's a team of 300 people writing them. Another company has a big R&D office in Toronto is called Cerebras. Has anybody heard of Cerebras? Okay, so a few people in the back anyway. So Cerebras is now hiring lots of my grad students actually. So they're hiring lots of people who work on integrated circuits and FPGAs. So what does Cerebras do? They make deep learning accelerators. So they're trying to train really big neural networks. And to do that, they said, forget about these chips. We're taking the whole wafer. Okay, so what's a wafer? Here's one of the wafers that of chips that I worked on when I was at Altera. Okay, this is an 8-inch wafer. So now the latest ones are 12-inch. But those ones are all framed at the Intel office because they're so pretty. Okay, so that's a wafer, except think of it 12 inches. Cerebras says we're not going to cut out the 400 chips you usually get. We are just going to make one giant chip, which is the size of the whole wafer. So that's why they're showing it as dinner plate size. It really is dinner plate size. It consumes 15 kilowatts of power, costs several $1 million for that one piece of silicon. It has 2.6 trillion transistors on it, 850,000 processor cores. Okay, so Stratix 10 had 10 million logic elements, like lookup tables. This thing has 850,000 processors on it. They have to be connected to collaborate to perform a deep learning training. So you need to connect millions of data transfers between these processor cores, which is basically the nodes are buses, 32-bit buses, and the edges are multiplexers between them. And you have to search for millions of paths through that in order to connect them in this huge graph. So you need super fast algorithms again. Okay, so these algorithms are actually very relevant in our field and in many other fields. And actually Cerebras is hiring PUI students as well. So one of my summer students from last year is about to go there. So you might wind up working at Cerebras as well if that interests you. Okay, thanks everybody. If there are any questions, I'll be up here at the front. We're thinking about the time now.